Chapter 5 then is about probabilities, and we start with a set of definitions which we need to be quite familiar with. It might seem like this is a sort of pointless first section, really. There's not very much in it that we've not seen before, but it's quite a good idea to get your head round exactly what these definitions mean. The experiment then in probability is what you're doing. You're rolling a dice, you're flipping a coin, what you're doing, and you're recording the result of that experiment. The outcomes are the individual results of the experiment. So if you're rolling a dice, the usual outcomes will be 1, 2, 3, 4, 5, or 6. If you are flipping a coin, the outcomes will be heads or tails. An event is one or more outcomes. So getting more than a 3 is an event, it's not an outcome. Okay, so there's a slight difference there. Sample space is the first one where I've seen it, I think, on exam paper questions. What is a sample space? So a sample space is just a list of all the possible outcomes. So you need to know the difference between an outcome and an event, so you don't start listing events instead of outcomes. A sample space is a list of all the possible outcomes, and equally likely outcomes means each of the outcomes has the same probability of occurring, and equally likely outcomes are fairly straightforward probability questions that hopefully we're familiar with. If you take an example of something like, I could say I buy a lottery ticket to see whether I win or not, the probability experiment would be buying a ticket, seeing whether I win. The outcomes would be winning or not winning. They're obviously not equally likely. So the outcomes for every experiment don't have to be equally likely. So just be careful with that one. Example 1. Very much GCSE example. This thing is called a sample space diagram. If you've got 2 experiments happening, you can put one on the x-axis, one on the y-axis. If the outcomes of the first experiment and the outcome of the second experiment are equally likely, then the outcomes in the sample space diagram are equally likely. So in this case, there are 16 possible outcomes, and we can solve those questions. I've said on the previous ones of these videos, I'm not aiming to recap GCSE material, so we'll carry straight on. So section 5.2 is Venn diagrams. Now, having just said I'm not going to recap GCSE material, I think this is now on the new GCSE syllabus, but I'm recording this in 2018 and I haven't actually taught the higher part of the new GCSE syllabus yet, so I can't remember exactly how much this is there and in what detail, so I'm going to recap through the Venn diagrams. Obviously, if you know it well from GCSE, you don't need to watch this part of the video. So, the idea here is we draw a little diagram to represent things that are happening, and we call those things events. Okay, so we've got event A and event B in here, and a typical example might be something like if we have a set of cards, a pack of cards, and I pick a card. Event A could be getting a heart, event B could be getting a 9. So in the bit here, in the overlap of the 2 circles, we're inside event A and we're inside event B, so that would be getting a 9 and a heart. So in the overlap would be the 9 of hearts. Outside event A and event B, out here in the rectangle, but not in the ovals, would be a card which is not a 9 and which is not a heart. Inside event A, did I say that A was getting a heart? So A would be all the hearts except the 9, and B would be all the 9s except the 9 of hearts in this area here, not in the overlap, okay? So it's that sort of idea. I'm sure you've met the idea of Venn diagrams before, at least. Now, this area there is called the intersection. A and B all together would be the union. So in our example, all the 9s and all the hearts, whether they're 9s or not doesn't matter, whether the 9s are hearts or not doesn't matter. So it would be the entire suit of hearts plus the 9 of clubs, spades and diamonds. And then a complement is everything outside of A's. So if A was the event getting a heart, then the yellow bit here is everything that's not in that set, so getting any other card as long as it's not a heart, okay? The notation that we need to be familiar with is A intersection B, A union B, and A complement. So A intersection B means event A and event B have both happened. So I always think of this as sort of an N for A and B. So event A and event B have both happened. A union B, either A's happened or B's happened, one or the other, or both it could be. I always think of that as a sort of like a trade union, everyone together. Well, here, everything in event A and everything in event B, all of it together. Intersection is like the overlap, okay? And the union is easy to remember because it's the sort of U-shapey symbol. A dash or not A, or A complement everything outside of set A. And that's the yellow shape on the diagram there. So the sort of questions that we get asked then. We've got example 3 and example 4 with Venn diagram questions here. Now you can see from example 3 and example 4, sometimes we put the frequencies in the sections of the Venn diagram, sometimes we put probabilities in there. It doesn't, strictly speaking, matter which. Either is fine as long as you're consistent all the way through the question, okay? Now I'm going to leave example 3 alone. We're going to go straight in for example 4. My advice is the following. Draw the Venn diagram out. Not absolutely always, but almost always. The best advice is to start with the most overlapping bit. So let's assume we can't see this here. We've got this vet with 100 clients, and they've got people that own cats or dogs or fish. This bit here in the middle, which we could, if we wanted, notate like this, D intersection C intersection F, is people that own dogs and cats and fish. So that bit there, if I can fill that bit in first, that will help me fill in the rest of it. So dogs and cats and fish, that's there it says is 7 people. And then go for the next most overlapping bit. So the most overlapping bit of the diagram first, and then work your way out. Not every question can you do that with, but on the whole, it's a good way of doing it. Even if you have to, even if that's the bit that you don't know, put an X in there, and then work your way out writing things in terms of X. That's usually the best way forward. So this bit here, well, this here that I'm sketching around now is dogs and cats. So that's D intersection C. That's all the people that own dogs and cats. 7 of those people are in this bit. So this bit here, well, dogs and cat owners is 15 people. So there must be 8 here because there's 15 in that section there. And we just work our way out in the same way. Now I'm putting frequencies. They've decided to put them as probabilities, and they're writing the probabilities as decimals in the example there. But it's that sort of technique that we're going to use. And the main idea, again, is do the most overlapping part first. Section 5.3, we've got mutually exclusive events. So mutually exclusive, the idea is they can't happen at the same time. So, for example, rolling a 3 on a dice and rolling a 4 on a dice, if you roll the 3, you can't have rolled the 4. The rolling a 3 means that you can't have got the 4. So those two things can't happen at the same time. If the events can't happen at the same time, there can't be an overlap. So by definition, if we've got mutually exclusive events, A intersection B, the probability of A intersection B is 0. There is no overlap. So that means the probability of getting A or B, that is the probability of, that's the same as the probability of A union B, is probability of A plus the probability of B. Okay, so the union, remember, means A happening or B happening. Usually there's an overlap, isn't there? Here's event A, here's event B. If I did probability of A plus the probability of B, I'd be counting this overlap, I'd be counting the intersection twice. So the general rule, which isn't actually in this textbook, but is just for interest, is the probability of A union B is the probability of A, probability of A plus the probability of B. If I do that, I've counted the union twice, sorry, counted the intersection twice, so I need to take away the intersection. But if I have mutually exclusive events, by definition, the intersection is 0. So for mutually exclusive events, I just cross that bit off, and I'm left with this rule here. And if you remember that union just means A or B, then that gives us the rule from the textbook. Easy to see that on the Venn diagram. A and B just don't overlap, okay? Now, independent events, the first thing with independent events is there is not an easy way to see that on the Venn diagram, okay? There's no sort of, you can't look at it and say, well, those two things don't overlap, or these things do overlap, or something like that. There's no easy way to see it on the Venn diagram. And the definition is the probability of A and B, or so A intersection B, is the probability of A times the probability of B. Oh, missed a bracket out there, okay? And it's the rule we're familiar with, the multiplication rule. If I have, what's the probability of getting a heads on a dice and a 3 on, sorry, a heads on a coin and a 3 on a dice? The probability of getting the heads is a half. and then I've got to roll the dice. The probability of getting the 3 is a sixth. Well, if you imagine doing those two things at the same time, a sixth of the time you're going to get the 3. Every time you get a 3, half of those times you're going to get the heads as well. So the probability of getting both happening at the same time is 1 times the other, okay? So that's independent events. And the idea is that independent events are events where one doesn't affect the other. So if I have something like in example 7 here, this is about students in a particular class watching TV programs. Well, if the TV programs are on at the same time, then somebody choosing to use one of them would mean they couldn't, somebody choosing to watch one would mean that they can't watch the other. So that would mean those choosing to watch one would be mutually exclusive watching the other. So it looks like A and C, look, there's no overlap, so they're mutually exclusive. It's not clear whether probability of watching A and B is independent, so it might be that that somebody watching one would affect the probability of them watching the other one. So for example, if, you know, when you get a TV program which has a sort of offshoot TV program, so you get you know, kind of Great British Bake Off and then the extra slice. Well, if you watch one, that might affect the probability of you watching the other because you might be more or less interested in it. But the probability of you watching, say, Great British Bake Off and football might be independent. Maybe watching one doesn't affect the chances of you watching the other at all. So independent events are not too obvious on the Venn diagram. Mutually exclusive events are. Those are the sort of examples we're looking at. The last thing on this chapter is the tree diagrams. I don't think we need to recap exactly how these work. It's definitely on the GCSE syllabus, and my principle is to not recap GCSE material here. What I do need to say here, though, with tree diagrams is, although we should know how tree diagrams work, hopefully we now know how Venn diagrams work. When you get a question on the exam, it's not always obvious what technique you're supposed to use in order to solve the question. Once you've decided that the question is a probability question, it's using the probability from chapter 5, there are 3 parts of chapter 5. There's tree diagrams, there are Venn diagrams, and then there's that little bit at the start where we're just looking at sample space diagrams, okay? Now, most of the questions, at least from the old syllabus, this is 2018, so we've just changed syllabus, but in the old syllabus, most of the questions were Venn diagrams or tree diagrams, and with the probability question, the difficulty was just knowing which diagram to draw. There are only 2 options. So if you know that you've got a probability question, but you're not sure exactly how to do it, pick Venn diagrams and try and turn it into a Venn diagram. If that's not working, pick a tree diagram, try and turn it into a tree diagram. If really neither of those are working, then maybe read the question again. Maybe it's giving you a hint that it's only a simple sample space diagram or something like that. Now, some of the questions will be obvious. So I'm just looking at question 5 here. It says draw a Venn diagram. Even if it didn't say draw a Venn diagram, looking through this sort of list is the sort of list they give us on Venn diagram kind of questions. So there's a hint in that sort of direction before we've even started, that, you know, before we even read that question, I'm looking at that list and I'm thinking that's probably a Venn diagram because I know it's a probability one. But a good hint for the exam is if you know it's a chapter 5 probability kind of a question and you're not sure whether you should do a tree diagram or a Venn diagram, well, try one. If it doesn't work, try the other, and hopefully one of the 2 things will work. There's only 2 techniques. You've got time to try both.